Hey, good morning or afternoon, everyone. The general topic here is our mid-latitude linkages. As you all know, the attribution issue here is very controversial. I think what has come out is probably no net impact, or that's fairly small, but and if there is a signal, it's buried in a lot of chaotic noise, so it makes for a difficult problem. Perhaps another subgroup we might want to have is just how do we present this to a broader audience, but especially for people who are not buried in the details, everyone thinks it's a great problem because it impacts where people live, and we have this working group, and I know TMO is working on something in the European Union. So so thinking about this over the last year, I think there's two ideas that are somewhat breaks through from the sort of status of not much progress that we've had over 4 working groups, and these were 3 papers, one by Ted Shepard and 2 led by Kevin Trimberth. And the first idea is that basically all or most of the chaotic random part of the variability is in the circulation and dynamics aspects, where the thermodynamics tend to be more robust, so that the idea is whether you have an extreme event or not depends on the circulation, which is mostly random, but then whether you have a amplification of that particular event depends upon the external forcing from the thermodynamic aspects. And a not unrelated issue is how to think of the overall question of having a short record, and this gets into thinking about the null hypothesis versus risk. And the basic problem for the short record is when you're setting up the significance test, that depends something on the variability of the process, which is the part you want to really constrain, but then it's also goes as 1 over the square root of the number of observations as well, and so when you have a short record, rather than the physical processes determining your significance, it's really governed by too few degrees of freedom. So you end up with this wide test band if you don't want to make a type 1 error of accepting something that's not there, and that's governed by the number of observations rather than the real physics. And so sort of channeling my best Kevin Trimberth here, the view then is that you're highly likely to make type 2 errors of not accepting something that was really there. And he actually goes even beyond that in the global change realm. We have global change is unequivocal, and so he would almost say that you should go to the other end where you're trying to prove that an effect wasn't there. But I mean, that has a wide band as well because of so few degrees of freedom. So those are the two kind of pieces there. In the Shepard paper, just circumstantially, he has the global temperature and sea ice being more thermodynamic variables, where the southern oscillation and rainfall are more of these dynamic variables, and the thermodynamics are also the ones that have the long-term external forcing to them that could act on more random circulation. The first place that I ran across this was a discussion several years ago from the Russian heat wave in 2010, and the top figure shows the height field. The colors are the anomalies, and the second one down is the surface temperature departure. And there were two really different papers about it. The first one was Randy Dole, who looked earlier than the heat wave by a week or so, and said, well, there were about 3 different dynamic processes that all fortuitously came together to make the heat wave, and so that there was very little predictability to the heat wave at all, just due to the random dynamics. The second paper talked that there was preconditioning involved with both the background global warming plus the trajectory of some of the warm air coming off of the Indian Ocean. And finally, the paper by Otto said, well, those are just 2 different ways of looking at the same thing, but it brings up this issue of thinking about circulation part, whether it occurs or not, being more random, but then how strong it is depends a lot on the thermodynamics, either preconditioning or reinforcing the pattern once you have it. And I think that's a real clue here. The 2 bottom panels there are some composites of other heat waves, and Dole had that to show that basically the Russian 2010 wasn't that extreme. He used that as a argument that 2010 was completely random, but I think that's not quite the right interpretation, and I'll come back to that on my last slide or so. I generally hate word slides, but I wanted to put this up and capture. These are words from Kent Trenberth's paper. His basic idea is that when there's an extreme event, people often point to anomalous circulation or storm tracks or blocking that cause extremes. And his view that that's not quite the right way to think about it, that those that the circulation is really part of the description of the extreme event, and he likes the idea of separating out the dynamics from the more thermodynamic. So you end up with a conditional or state-dependent view of that. So he suggests having conditional statements. So, given the weather pattern, how did the temperatures and precipitation amplify the impacts? And if you had a drought or a heat wave, what might have been some of the preconditioning that would amplify something that's already started? And that's sort of my main viewpoint here, too. And in the 2014 paper, he had quite a few major examples. The spring snow Armageddon on the East Coast, the dynamics was the cold air met ENSO, but you also had a moisture source for the heavy snow from the SST fields. The Boulder flood was a strong atmospheric river flow atmospheric river flow coming off the Pacific, but then Kevin said that there were some moisture sources as well that came up from the subtropics that did relate to a global warming. The recent California drought is really a North Pacific SST, and there's an amplification of the ridging. But he also points out that the dryness of the ground and so on was a preconditioning. So to me, pointing out this way, it's fairly obvious, but there's actually a big semantic problem here, because in a lot of these, the question that's often put is, did global warming have an impact? And the people on the dynamic side have a resounding no. It was all random, and global warming had no effect. And that's in the literature on the Boulder flood and in the California drought for sure, where I think Kevin's view would be that we already have a background global warming, and so that any effect, any storm now is in a different environment than it was 20 or 30 years ago. So, but I think in terms of how we move forward and thinking about it, I like this conditional idea of separating out the more chaotic part from a thermodynamic forcing part. And to look a little bit then on the Arctic and subarctic, these are the time series for November, December, and January of the Arctic oscillation. It's just one number, but when the magnitudes are really large, you really do tend to have a zonal versus a meridional type circulation. These all show an upward trend from the 1980s to the 1990s. I was certainly around then, and there were papers showing that was statistically significant and must have been global warming, and the models showed global warming, but that all kind of fell apart. The two takeaways that I want you to see from here is that the variance in the lower panels is quite a bit smaller in November than December. So when we're thinking about forcing the general circulation, the sort of early winter circulation really isn't set up until December. So, while some of the heat flux and loss of ice, might be more November and October, the real impact on the circulation really couldn't happen until December. The other thing is that we see a statistically significant increase in the variance in the last decade, and we're not saying that is out of the range of natural variability, but it does point out that if you look at the top figure in December, rather than a downward trend in the AO or something like that, the real picture here is heightened variability. Whether that's random or some cause, we don't know, but certainly in the last decade we've had large extremes, both positive and negative, and that sets up this idea of conditional variability. So if you divide in the last decade, if you divide the 3 strong negative AO and the 3 strong positive AO Decembers, the upper left figure is the mean height field, and if you look at the height anomalies for the positive ones, you just reinforce the circulation. You reinforce the gradients and have an even stronger jet. So any kind of circulation feature embedded in the steering wind is just blown downstream. There's not enough time for secondary effects to develop. But if you look in the upper right figure, you have higher heights in the negative AO pattern, and they're occurring at the same place as the mean height. So we're not really talking about an AO circulation pattern. We're really just it's just really a modification of the mean flow. But when you get to the negative AO pattern, the lower right shows the strong meridional character with northerly winds over the eastern United States, bringing that down, and actually some southerlies going up Baffin Bay. And so if you look at the difference of the patterns in terms of thickness, the minus AO has large, warm geopotential thickness in the lower half of the atmosphere that you have to go along with those anomalous heights over northeast Canada and Baffin Bay. And finally, we're seeing on the right is the low level temperatures, and there's a lot of support for the increased thickness and height from the low level temperatures. So we would say that in terms of conditional pattern, if you have the plus AO, you have the strong zonal winds, there's not enough time for anything to develop. You just blow everything through, where In the negative AO, you have some time for the local low-level support to help reinforce that the thickness pattern, and then the change in the circulation that brings those cold air southward over the U.S. So rather than just kind of a linear thinking, it's really a nonlinear condition based on what the circulation pattern starts out with. Finally, a little bit more on this null hypothesis that due to lack of observations, that the hypothesis testing is limited by the number of degrees of freedom rather than something about the variability of the physics itself, which is a rather difficult and not very well appreciated piece. So it's more the mechanics than the physics, and because of that, normal hypothesis testing, is there an effect? You open yourselves wide open to large type 2 errors, and then that gets into Kevin's point about, I think, both for global warming but also for the Arctic, that we have a strong prior that we know that there are large warming events in the Arctic, and we're warming 2 to 3 times faster there. So that says, so you can set things up on trying to prove that something's there, or you can set it up proving something isn't there, but either one is dominated by too large testing bands due to the lack of observations. And then even more troubling than that is if we think about this conditionality place and the plus AO versus the minus AO and so on, we've got something really non-linear, and so using normal linear statistics to try and pull something out probably isn't a good way of thinking about it. Finally, I wanted to bring up one other point. You've all sort of seen these plots where you shift the distribution so you end up with more extreme values. But I think the big thing here for me, if you look at the lower one, look at the blue area above the black line, and those are large events that are not larger than really occurred before, but they're much more frequent. And so it's easy to talk about whether you have an all-time new event, but if you have large events, are they that have occurred before, and you have a new one, is that just the same as what we had before, or this seems to say that those large but not extreme events are much more common, and if you had a long time series or good models, you could determine whether it's more frequent or not. But again, when you have the short record of 10 years or so, you can't really say if you have one of these major events that's occurred before, whether that's actually more frequent or not. And so I think that goes against the Russian heat wave idea that, well, if you've seen it before, it's not necessarily caused by something new. I would say that it's not unreasonable to accept either hypothesis, and you can't really tell the difference. And so that's where whether you have the risk avoidance approach or not is important. So in summary, Shepard and Trimber bring up the idea that most of the chaotic internal variability, whether an extreme event happens or not, is in the circulation, and it's fairly random on that. But then the thermodynamics, whether you have a warmer Arctic or loss of sea ice, comes out that it doesn't cause the event, but it can feed into whether the event is stronger than it might be. And I think there's some there's some indication that we may be seeing a little bit of that in the increased variability on the East Coast. And finally, on the risk avoidance point is we really need to wonder about, if we have hypothesis testing and say it doesn't satisfy the hypothesis, that's generally interpreted to mean that there's something in the physics that we can't really see the difference, where with a short time series, it's really the lack of degrees of freedom that are what you're testing for, not whether it's a physical outlier or not. And so we end up with the idea of large type 2 errors, and so this is where the idea of the priors come in, that if we accept that we're already in a new normal or new regime, that simply going with the null hypothesis of no effect isn't the only way to think about that. So thanks a lot, and I'll appreciate any comments. There's certainly thought here.
The conference has been unmuted.
Great. Hi there.
Yes, I just want to thank Jim for volunteering to give the first presentation for the webinar. It's definitely I thought it was. Are we okay now?
Okay, I tried to mute a couple people who I think may have been causing some noise. Yeah, that's the problem when I take everyone off mute. So I think we're okay. I think, Ron, you were having some feedback. I muted you and it seemed to stop it. So go ahead, Judah.
Yeah, that's one again. I want to thank Jim for starting it off. I thought it was a good, get a good overview of some of the problems with detection of the Arctic influence, and I guess still as a group we need to, so not today, but we're going to need to try to make progress on this. How do we get how do we answer this question with the limited observations that we do have? So we're not, this topic it just ended with Jim's talk. I do think it's a bit ironic, Jim, that you using Kevin Trember to kind of advocate that there is room for the Arctic in mid-latitude weather, when Kevin Trenberth himself would say there is no influence whatsoever from the Arctic and mid-latitude weather, but certainly we could use his ideas anyway.
Yeah, that's one of the paradoxes here, but I think his argument is that the Arctic is so small compared to the tropics. But again, if we're thinking of regional impacts, I think that opens up the Arctic again.
Right. Yeah. Yeah. Okay.
And Judah, looks like Arun has a question. He's raised his hand.
Okay. Yeah. Sure.
You have time?
Yeah.
Oh, okay. Thanks, Jim, for the presentation. It was a very nice summary. One comment I would like, and then a question I'd like to get your view on it. So, one of the reasons, at least in the seasonal time scale, one of the reasons of doing the attribution is that you can connect it to predictions. So, attribution is connecting something to something else. One of the classic examples is the paper by Hurl and Wallace, which shows you can, even in 1982, there was very little data. You can connect the PNA anomalies with the ENSO, and that set the theme for entire seasonal prediction effort and where we are today. So if you take the dynamical view, which says that things haven't changed, or so that says that the prospects of doing the predictions based on attribution would be very small. But if you take the thermodynamic view, it says if things are happening, if some dynamical feature is there and global change has occurred, then a same circulation will give you, let's say, higher temperature anomalies or higher precipitation. So one view says that if you cannot use the information in doing any or improving the prediction, while others say that, okay, when there's something happening, you can tell the extremes would be higher. So any comments on that, or?
Yeah, I think in looking at the North Pacific, we looked at the North Pacific and Alaska, and there's something they like to call El Nino North, and it turns out if you have a real strong zonal flow across the northern North Pacific, that the teleconnection isn't there, but if you have a weaker zonal flow, then the El Nino teleconnection can actually propagate north. So I really like this conditional idea that if you have one circulation type, you can have the teleconnection, and but if you have the strong zonal circulation type, it would be much weaker or non-existent.
But that doesn't help you in predicting anything about the circulation itself.
Well, if you think it's only in the probabilistic sense, that if you think the thermodynamics is there's a higher probability, but then it's a dice roll on which circulation regime you have.
Okay, thanks.
But I mean, maybe not so much anymore, but I mean, isn't in a certain way CPC using that conditional thermodynamic change to bias, let's say, a warmer forecast, almost regardless of the circulation that's being anticipated?
Yeah, so we have a prediction tool which is based on the trends, and that's kind of a static thing. So since last 10 years have been warm compared to last 30 years, so we take that into account, making the prediction every season. But that does not depend upon any information about what the circulation may be. You just add that on top of the circulation. So it's like the last plot on the PDF.
Right.
The last plot Jim was showing that you expect everything to be warmer, so you just use that for prediction.
Yeah.
But I think the large variability of the AO plus and the AO minus really helps us out here. That you don't have a trend towards either circulation type, but we've all been watching those. When it came on the positive AO year, it was just a real strong zonal flow, and you were either north or south of the jet, and that was it. Where in the minus AO years, you had a more wavy jet stream and to work with, and everything was slowing down a bit. So, it's an either or in different years reinforces this conditional idea.
Yeah.
I guess, Jim, thinking about your presentation, I think we can borrow from maybe the similar arguments for, like, sense in the Russian heat wave. That's not necessarily Arctic mid-latitude relationship, but it's looking at natural versus forced variability. And, we're supposed to have this bibliography. I don't know if it's gotten started yet, different papers that are related, to this topic. But, I guess we could include some of these papers that are not necessarily, or even the Kevin Tremberth, which is not, again, dealing with Arctic, but more, the global warming. And we can see how they try to, also try to deal with this natural versus forest with, limited observations. And I guess it's something that we could maybe try to borrow and then improve upon or suggest further. About how we could apply this for the Arctic mid-latitude problem. And I guess I'm looking at if someone can maybe help identify those papers that are not necessarily Arctic, but would help us with this issue of the short observational record.
That's good. Plus on the Russian heat wave, you end up weakening the Siberian high, so there is a component that is coming down from the Arctic side on that, and my reading of it was part Arctic plus part coming in from the west, and that the East Coast is a bit that way too.
Okay, I don't go off on a tangent. I'm not sure what you mean by Siberian high. The Siberian high only gets going in October, so
yeah.
This is July.
Yeah.
Not really.
I believe it's anomaly so high. Yeah.
There's a strong anomalous high, but it's not the Siberian high that we classically think of. That is really a winter phenomenon.
Mm-hmm.
But the airflow, up around the Kara Sea seems to be a special forcing reason.
Yeah, no, absolutely. But
there's a couple of questions online, so maybe we want to take these other people who have their hands up and then move on so we can take care of business before 3 o'clock.
Can we end this in an hour? I guess that's...
Yeah. So let's take these last two questions and keep them short, and then you guys can have some time to focus on the last few business items. So, Ron, you had your hand up, and then TMO.
Okay.
Ron, I don't know is your audio connected?
Can you hear me?
Yes, go ahead.
Okay. So Jim, what is the latest on trends in the AO? You showed perhaps for December there's increased variability, but there are different sort of spatial lobes in the AO. Is that anything that anybody's looked at? That's more AO dynamics.
Yeah, that's a good question, and the only normally I wouldn't go with the AO because it's just one number, but when we had such an extreme positive and negative, it really is a art-wide issue. So I wrote dropping it down. I think it, which side of the Arctic has the biggest effect, varies from year to year and so on. Someone else might have an idea.
Well, I mean, I didn't fully hear the question, but
I guess my question was there any for aerodynamics? What's warming doing to the AO signature in terms of whether there's any evolution in that sort of stationary pattern that we usually look at?
Yeah. Can I provide my comments?
Yeah, sure.
Hello. Okay. Yeah. Well, from my understanding, because we look at the AO, so from my understanding, AO is just the representation of a circulation pattern. It's not itself. It's not a physics. So when we look at the AO fluctuates year by year, month by month. So we look at the people talk about the global warming, temperature changes, and the circulation fluctuation. From my understanding, the circulation, the change, for example, changes of the AO, that changes the wind pattern and the redistribute the heat. Right? That could provide the temperature changes in particular area, particular region. Yeah.
Yeah. So what I was trying to say is on the three large negative AO examples we did have a big zone or a meridional wind effect over North America. So I was just using it in that, but I think in those cases, if you looked at the height pattern, there was actually a bigger meridional component in the Eurasian part. So one of the things, and this actually gets into the Hurricane Sandy part, is we had sort of three lobes of higher heights over the Central Arctic. So, an outstanding issue is how much is regional and how much is tied with wave number 3 to 5.
Yeah, I guess I like the example that you show of the AO in connection to your discussion about conditional statistics.
Yeah, and so from that you would say the AO is mostly random circulation.
Okay, thanks.
Great. We have one more question from TMO, so let's take this one and then we'll wrap it up and let Judah and Zhangdong wrap up business.
Okay,
TMO, go ahead.
you. Do you hear me?
Yes, go ahead.
Do you hear me? Okay,
Yeah.
so this point of view that Kevin Trenberg and Ted Shepard have presented that thermodynamic effects of climate change tend to be robust, but dynamic ones are usually chaotic and not so robust. I think it's an important point of view, but isn't it a little bit too categorical division? Because if we think about the Arctic warming effects on mid-latitude circulation, there is this very important weakening of the zonal flow that directly results from the thermal wind. So it's kind of a dynamic effect that has a very clear thermodynamic origin, and therefore it's not just a chaotic influence. So I think that Kevin Trenberg, at least in this 2014 paper, has been a little bit too skeptical about the Arctic dynamic influences of Arctic on mid-latitudes. What do you think?
Well, you kind of caught me out because I think this.
Hey Jim, could you repeat? I couldn't hear Tim's question.
Well, what he was saying is that with an overall weakening of the jet and a tie with the thermal wind, that there could be a change in the circulation that is caused directly by the warming of the Arctic. And you kind of caught me out, Timo, because I think this conditional approach works fairly well north of or in North America, but in the winter Kara Sea area, we do know that the loss of sea ice and the warming there has reduced the jet, so there is a direct impact of the thermodynamics on the circulation rather than the circulation just being all random. So more complexity based on region, I think.
Yeah.
Okay, all right. So try to get this teleconference wrapped up.